Welcome back. So this is a short video just to recap this module on dynamic instruction scheduling, Thomas Wheeler's algorithm, as well as the big high-level concepts. So we have been studying dynamic instruction scheduling, also known as out-of-order execution. Now the goal is to achieve higher pipeline or functional unit utilization. Let's see if we can keep those functional units as close to 100% utilized as we can. And the better utilized the pipeline, the better our performance will be. We'll have higher instructions per cycle, higher instruction throughput, and therefore lower average CPI. Now, dynamic instruction scheduling is easier and more effective in hardware than in software. I made some brief arguments about why static instruction scheduling is possible with techniques such as loop unrolling. Software pipelining is another approach, where the compiler or maybe the programmer would try to reorder instructions to fill in the delay slots, those cycles that are known to be stalls. For example, a load to use stall. Can we fill that useless cycle with some other useful instruction? But with hardware, we have two big advantages, along with others. First, we can control the number of storage locations. We can offer more storage locations for data, for registers, than the set of defined architectural registers in the ISA. The compiler, the programmer, the only names that they have to play with are those in the ISA, limiting their ability to perform register renaming. Now, another key feature is that in hardware, we can dynamically handle variable latency instructions like cache misses, whereas the compiler, it would have a tough time knowing for some given load or store whether it would result in a hit or a miss. But hardware, we can adapt on the fly to long latency instructions and try to execute younger, independent instructions to keep the pipeline well utilized. So we saw that the key idea of dynamic instruction scheduling is that of a instruction buffer, a conceptual instruction buffer that we viewed abstractly as multiple latches between the fetch and decode stages. This conceptual instruction buffer, it implements a large scheduling scope, and it enables a passing functionality so that young instructions can pass older ones that are blocked on long latency execution. In contrast with that 5-stage in-order pipeline, we had one FD latch, and thus the pipeline structurally prevented instructions from passing one another into the execute stage. They would have clobbered each other's data in a single FD latch. To use this instruction buffer, we conceptually split the decode into two stages, an in-order dispatch and an out-of-order issue. We saw that several stages in the pipeline remained the same and others changed. And we started to learn about two different terms that seem related, stalling versus waiting. So stalls, which propagate the delay, the stall, to younger instructions, versus waiting, where an instruction can sit in some buffer while younger instructions can pass around it and use resources, functional units, more effectively. Now, there are more dynamic instruction scheduling algorithms out there, and in this module, we focused on one implementation, Thomas Wheeler's algorithm, or Thomas Wheeler's organization, which uses copy-based register renaming and is fully out of order for its execution and even write-back of registers. At the end of the last video, I gave you a little hint that out-of-order write-back is going to be a problem for maintaining precise state when we face exceptions and interrupts, and in fact, even for control speculation. So what we're going to see in the next module is how to augment what we've learned so far about out-of-order execution to properly handle precise state and control speculation. We need a means of recovery. So I will see you there.